In this lecture, we will study algebra of convergent sequences. So let us see few results in algebra of convergent sequences. Algebra of convergent sequences of real numbers. Theorem: the sum of two convergent sequences is again a convergent sequence of real numbers, and sum of their limit is limit of their sum. Let Sn n is equal to 1 to infinity and Tn n is equal to 1 to infinity be convergent sequences of real numbers then the sequence Sn plus Tn is also convergent, and limit of sum Sn plus Tn equals to sum of limits limit Sn and limit Tn. So sum of two convergent sequences is convergent and limit of sum is sum of limits. This result we have. So in order to prove this result, we are going to use definition of limit of a sequence. Take epsilon greater than 0. We begin by taking some epsilon greater than 0. Let limit of Sn as n tends to infinity equal to L and limit of Tn as n tends to infinity equal to m. By definition of limit of a sequence, by definition of limit of a sequence, there is n1 belongs to I denotes the set of positive integers. So there is n1 belongs to I such that n is greater equal to n1 implies mod Sn minus L is less than epsilon. As epsilon is arbitrary, we can replace epsilon by any expression which will result in arbitrary positive number. For example, I can replace epsilon by 2 epsilon, I can replace by epsilon square root epsilon. Because epsilon is arbitrarily positive number, I can replace epsilon by any suitable expression which results into positive real number. So in this case, I am going to select epsilon by 2. Again, this choice need not be unique. You may have different choices. I'll also explain it once I complete the proof. Similarly, or better let me continue with this. So this follows from the definition of limit of Sn and it is equal to L. Similarly, as limit of Tn as n tends to infinity is equal to m, there is n2 belongs to I, there is n2 belongs to I such that n is greater equal to n2 implies mod Tn minus m is less than epsilon, and as I mentioned I can make this to be epsilon by 2, or I can replace epsilon by 2 as epsilon is arbitrary. Now try to understand meaning of these two statements clearly. What the first statement says, if n is greater equal to n1, then distance between Sn and L is less than epsilon by 2. So which values n can assume? N can assume the value say n1, n1 plus 1, n1 plus 2 and so on. Similarly, what this second statement states that if n is greater equal to n2, then distance between Tn and m is less than epsilon by 2. And what values we can assign to this n? We can assign n to be n2, n2 plus 1, n2 plus 2 and so on. So these values we can assign. Now what I want that these statements to hold simultaneously. So in order that these two statements hold simultaneously, I can select any number which is greater than or equal to n1 and n2. For example, if n1 is say 100, then these values will be 100, 101, 102 and so on. If n2 is say 200, then these values will be 200, 201, 202 and so on. Okay. What I want that these two statements Sn minus L, mod Sn minus L is less than epsilon by 2 and mod Tn minus m is less than epsilon by 2, both should hold simultaneously, and in order that these two statements hold simultaneously, I have to take maximum or any number which is greater equal to 200. So the simplest choice would be maximum. Say if I observe that 200, 201, 202 they are going to appear here, but 100, 101 are not going to appear here. That's why we need a number which is greater than n1 and n2, and we can take it as maximum. So in this case I could take 200 and then these two statements will hold simultaneously. Okay. So in order that this statement and this statement hold simultaneously, I select n to be maximum. Take n is equal to maximum of n1 and n2. Then n is greater equal to n implies that both statements hold simultaneously, that is mod Sn minus L is less than epsilon by 2 and mod Sn minus m is less than epsilon by 2. This implies n is greater equal to n implies mod Sn minus L plus, sorry, I should write here mod Tn minus m plus mod Tn minus m is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. This implies use triangle inequality. So n is greater equal to n implies that mod Sn minus L plus mod plus Tn minus M mod is less than epsilon. The reason is since mod A plus B is less equal to mod A plus mod B. So we are using triangle inequality. This expression is less equal to this, and as this is less than epsilon, this will also be less than epsilon. So this implies that n is greater equal to n implies mod Sn plus Tn minus L plus M is less than epsilon. Thus, for every epsilon greater than 0, we have found an n belongs to I such that this condition gets satisfied. Hence, by definition of limit, we can say that by definition of limit, we can prove that, or we can say that limit of Sn plus Tn equals to L plus M, which is nothing but limit of Sn plus limit of Tn. So this I can write as limit of Sn plus limit of Tn, limit of Tn. This completes the proof. There is exactly the similar result for difference of two convergent sequences. The result goes like this. Then if Sn and Tn are convergent sequences of real numbers, then Sn minus Tn is also convergent, and further limit of difference is difference of limits, that is limit of Sn minus Tn equals to limit Sn minus limit Tn. Okay, so proof is almost similar except for this fact. So we begin by taking epsilon greater than 0. There exists n1 satisfying this property, there is n2 satisfying this property. We take maximum. So up to this point the proof is going to be similar. In fact, up to this point proof is going to be similar. Just here we will have to make a difference. The slight change is this, and you know that mod A minus B is also less equal to mod A plus B. So that is the only change which we have to make, and this will give us our required result, Sn minus Tn minus L minus M, and by definition of limit it will follow that limit of Sn minus Tn is equal to L minus M and L minus M. So proof is similar. With this slight change you can have this proof. Okay, so Sn minus Tn minus L minus M. Can go through the proof. It is going to be similar. This is correct, and mod A minus B is less equal to mod A plus mod B. So A is mod Sn minus L and B is Tn minus M. Okay, so mod A minus B. A is Sn minus L and B is this mod A plus mod B. Okay, let us see one simple result in this topic, algebra of convergent sequences of real numbers. Let Sn, n is equal to 1 to infinity. B, a convergent sequence. B, a convergent sequence of real numbers. Then Sn n is equal to 1 to infinity is, then I mean this, mod Sn. So if Sn is convergent, then mod Sn n is equal to 1 to infinity is convergent, and further limit of mod Sn equals to mod of limit Sn. So limit of modulus is modulus of limit. Proof. We give a direct proof here. What is direct proof of conditional statement? We have to prove P implies Q. What is P? P is the statement that L is equal to limit of mod Sn. So take L is equal to limit of Sn, and the statement Q is limit of mod Sn is mod L. So we begin with this. Then by definition of limit, we are directly using definition of limit. Then for every epsilon greater than 0, there exists n belongs to I such that if whenever n is greater or equal to n, distance between Sn and L is less than epsilon. Mod Sn minus L is less than epsilon. This implies for every epsilon greater than 0, there exists n belongs to I such that whenever n is greater or equal to n, distance between mod Sn minus mod L is also less than epsilon. Why is it? We are using this property. Mod of mod A minus mod B is always less equal to mod A minus B. So what is A? A is Sn, B is L, and this property we are using. And if you observe this, this is nothing but the definition of limit. Limit of mod Sn is mod L. So this implies limit of mod Sn equals to mod L, which is nothing but mod of limit Sn. So this is what we wish to prove. Proof is quite simple, but make sure that you understand this. So we'll see some more results in next lecture. Thank you.